You are moving right now, not because you shifted position or adjusted your pillow, not because you are restless or uncomfortable. You are moving because you cannot stop, because no object on Earth has ever been truly still. Not for a single moment in the 4.5 billion years this planet has existed. As you lie here, Earth is rotating at roughly 1,670 kilometers per hour at the equator. It is carrying you, along with everyone you have ever known, in its annual orbit around the Sun at approximately 107,000 kilometers per hour. The Sun itself is moving around the center of the Milky Way at roughly 800,000 kilometers per hour, a journey that takes roughly 230 million years to complete a single orbit. And the Milky Way, our entire galaxy, with its hundreds of billions of stars and everything that has ever lived on any of them, is falling toward a massive and still mysterious concentration of matter that astronomers call the Great Attractor at something approaching 2.2 million kilometers per hour. You are the most still you will ever be, and you are moving faster than any object ever built by human hands has ever traveled. That is what it means to live in a universe. And tonight, for the next 100 minutes, we are going to learn about ours, not the cold, technical universe of equations and data tables. The universe as a place, vast beyond imagining, occasionally violent, full of structures so enormous and events so strange that the human mind cannot hold them for long without slipping into something that feels almost like wonder. The universe that began 13.8 billion years ago from something smaller than any word we have for small, and that somehow, against all reasonable expectation, produced stars and planets and oceans and minds, and this particular moment in which you are lying here, listening, trying to fall asleep. My name is your host, and this is Sleepy Science Stories. I am so glad you found your way here. Whether today was long or short, full or empty, loud or too quiet, this time is yours. If these slow journeys through extraordinary things bring you comfort, please consider subscribing. It helps this quiet community of curious sleepers find each other, one night at a time. Now let your body go heavy. Let the motion you cannot feel carry you where it always has. And let's go somewhere vast and beautiful and strange. Let's go to our universe. The observable universe is not the whole universe, and the part we cannot see may be infinite. When astronomers describe the size of the universe, they are describing something specific. The observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang. That sphere has a radius of approximately 46 billion light years, not 13.8 billion as you might expect from the universe's age, but 46 billion because the universe has been expanding during all the time that light has been traveling. Every direction you look from where you are lying right now, space extends for 46 billion light years before reaching the edge of what can, in principle, be seen. Beyond that edge is not a wall, not emptiness, not the end of anything. It is simply more universe, continuing in all directions, containing more galaxies, more stars, more worlds, an amount of more that our mathematics can describe and our minds genuinely cannot. The observable universe contains roughly 2 trillion galaxies, a number revised dramatically upward from the previous estimate of 200 billion when deeper surveys were conducted. 2 trillion galaxies, each containing hundreds of billions of stars on average. And this is only the part we can see. The actual universe may be many times larger. It may be infinite. Cosmologists use the word infinite carefully, but they use it. And what lies beyond our cosmic horizon, the regions of space from which light will never reach us because they are receding faster than light can travel, may contain copies of everything that exists here, repeated across distances too large for any number to name. The universe we can see is not the universe. It is a window, a small one. The Big Bang was not an explosion. It was something far stranger. Space itself beginning to exist. The name is wrong, and the physicist Fred Hoyle, who coined it sarcastically in 1949, did not intend it as a compliment. The Big Bang was not an explosion in space. There was no space for it to explode into, and no pre-existing void that it expanded through. The Big Bang was the beginning of space itself, the moment before which the concept of before may not have meaning, and the event in which space, time, matter, and energy began as a single unified state and immediately began to expand. In the first fraction of a second, the universe passed through temperatures and densities that make the interiors of the hottest stars seem cold. In the first 3 minutes, protons and neutrons combined to form the nuclei of hydrogen and helium. For roughly the next 380,000 years, the universe was so hot and dense that light could not travel freely through it. The entire cosmos was opaque. And then, as it continued to cool, electrons joined nuclei to form the first atoms, and the universe became transparent for the first time. The light released in that moment has been traveling ever since. We can still detect it. It reaches our instruments as a faint, uniform glow across the entire sky at a temperature of 2.725 degrees above absolute zero, called the cosmic microwave background. It is the oldest light in the universe. It is a photograph of the cosmos at 380,000 years old, and it contains, in its tiny temperature variations, ripples of 1 part in 100,000, the seeds of every galaxy, every star, and every world that would ever exist. The cosmic microwave background is a photograph of the universe at 380,000 years old, and it is still arriving. If you could see microwave radiation the way you see visible light, the entire sky would glow, not in the colors of a sunset or a nebula, but in a smooth, nearly uniform warmth arriving from every direction simultaneously. The afterglow of a universe that was once a single hot, dense, luminous place. The cosmic microwave background, first detected accidentally in 1964 by Arno Penzias and Robert Wilson, who initially thought it was interference from pigeon droppings on their antenna, is the most precisely measured light in science. The European Space Agency's Planck satellite mapped it in extraordinary detail between 2009 and 2013, revealing temperature variations of 1 part in 100,000 degrees, tiny fluctuations that represent regions of slightly higher density in the early universe. These regions were the gravitational seeds of everything. Where matter was slightly more concentrated, gravity pulled in more matter. Over hundreds of millions of years, these tiny fluctuations grew into the first stars, the first galaxies, the vast cosmic web of filaments and voids that structures the universe today. The entire architecture of the observable universe, every galaxy, every cluster, every supercluster, grew from variations smaller than the ones that make 2 snowflakes slightly different from each other. The faint glow that fills the sky tonight is not background noise. It is the oldest message in existence, sent before any star had yet been born, arriving still, now, from every direction at once, from a universe that was once too young to be dark. The first stars were made of nothing but hydrogen and helium, and they were unlike anything that has existed since. Every element heavier than helium, every carbon atom in your body, every oxygen molecule in your lungs, every iron atom in your blood, was forged inside a star and released when that star died. But the very first stars had none of this. They formed from the pure hydrogen and helium that emerged from the Big Bang, with no heavier elements at all, in an era astronomers call cosmic dawn. These first stars, sometimes called population 3 stars, are theorized to have been extraordinarily massive, tens to hundreds of times the mass of our Sun in many theoretical models. Because without heavier elements to radiate heat efficiently, the collapsing gas clouds grew enormous before nuclear fusion could ignite. They burned hot and fast and died young, their lifetimes measured in millions of years rather than billions. But when they died, in supernovae so bright they might have outshone entire young galaxies, they seeded the universe with the first heavy elements: carbon, oxygen, nitrogen, silicon, iron. The second generation of stars, born from clouds enriched by these deaths, were different. They could form planets. They could, in principle, harbor chemistry. The third generation, to which our Sun belongs, inherited all of that enrichment. You are, in the most literal sense, made of material that was processed inside at least 2 previous generations of stars before it became the solar nebula that eventually became you. The universe had to die twice to build you, and it did, without knowing you were coming. Where stars are born looks like the most beautiful place in the universe, and the James Webb Space Telescope showed us for the first time what it actually looks like. Stellar nurseries are regions of gas and dust where gravity slowly wins its long argument against pressure and temperature, collapsing molecular clouds into dense cores that eventually ignite as new stars. They have always been difficult to observe because the dust that surrounds newborn stars absorbs visible light, hiding the birth from optical telescopes. The Hubble Space Telescope captured the iconic Pillars of Creation image in 1995, towering columns of gas in the Eagle Nebula, one of the most reproduced astronomical images ever taken. In 2022, the James Webb Space Telescope, designed to see an infrared light that penetrates dust, captured the same pillars and revealed an entirely different universe hidden inside them. Hundreds of newly forming stars, invisible in Hubble's image, glowing in the infrared across the pillars and their edges. Protostars so young they have not yet ignited nuclear fusion, their light coming from the heat of gravitational collapse. The largest pillar in the Webb image is approximately 4 light-years tall, roughly the distance from our Sun to the nearest star. Inside it, something is happening that has been happening across the universe for 13 billion years. Hydrogen and helium, pulled together by nothing but gravity, growing dense enough to catch fire. The universe is still making stars. About 1 new star is born in the Milky Way roughly every year. They form in the same way they always have. And they are as beautiful as they have always been, now that we can finally see them. Neutron stars are the densest objects in the universe that we can actually observe, and a single teaspoon of one would weigh about 1 billion tons. When a star between roughly 8 and 20 times the mass of our Sun exhausts its nuclear fuel, it collapses in milliseconds, then explodes in a supernova that briefly outshines its entire galaxy. What remains at the center is a neutron star, an object typically about 20 kilometers in diameter, roughly the size of a city, containing between 1.2 and 2.2 times the mass of our entire Sun. The collapse is so extreme that electrons are forced into protons, converting them to neutrons, until the entire object is essentially a single atomic nucleus the size of a metropolis. A teaspoon of neutron star material, 5 milliliters, would weigh approximately 1 billion tons on Earth. The density is so extraordinary that a neutron star's surface gravity is around 200 billion times Earth's. The escape velocity at its surface is roughly half the speed of light. Neutron stars also spin, sometimes hundreds of times per second, emitting beams of radio waves like cosmic lighthouses as they rotate. These are called pulsars, and they are so metronomically regular in their timing that the first one discovered in 1967 by Jocelyn Bell Burnell was initially designated LGM1 for Little Green Men, because no natural process was imagined to be capable of such regularity. Neutron stars have since become among the most precisely studied objects in astrophysics, used to test theories of gravity, measure cosmic distances, and detect gravitational waves. The city-sized remnant of a dead star, spinning 700 times per second in the dark, ticking. Magnetars are neutron stars with magnetic fields so strong that from 1,000 miles away, they would erase every credit card, disrupt every electronic device, and alter the chemistry of your body. Neutron stars are already extreme, beyond easy comprehension. Magnetars are neutron stars with magnetic fields that have been amplified to levels that make ordinary neutron stars seem mundane. A typical magnetar has a magnetic field of approximately 100 billion Tesla. For comparison, the Earth's magnetic field is about 0.00005 Tesla. A hospital MRI machine operates at 1.5 to 3 Tesla. The magnet used to compress fuel in experimental fusion reactors reaches about 45 Tesla, which is considered a significant engineering achievement. A magnetar's field is 100 billion Tesla. At a distance of 1,000 kilometers from a magnetar, roughly the distance from New York to Chicago, its magnetic field would be strong enough to disrupt the iron in your blood, alter the chemistry of your cells, and destroy any electronic device. If a magnetar existed within about 10 light-years of Earth, its occasional flares, gamma-ray bursts caused by starquakes on its rigid crust, would be capable of stripping away portions of the atmosphere. The nearest known magnetar is approximately 50,000 light-years away, safely across the galaxy. On December 27, 2004, a magnetar called SGR 1806-2 released a flare that, despite being 50,000 light-years distant, measurably ionized Earth's upper atmosphere and produced the brightest gamma-ray flash ever recorded from beyond our solar system. The flash lasted 0.2 seconds. In that fifth of a second, it released more energy than our sun releases in 250,000 years. It came from a dead star smaller than any city. It had been dead for millions of years, and it was still, briefly, magnificent. Gravitational waves, ripples in the fabric of space itself, were detected for the first time in 2015, and in 2023 we heard the background hum of the entire universe for the first time. Albert Einstein predicted gravitational waves in 1916 as a consequence of his general theory of relativity. Massive accelerating objects should create ripples in the fabric of space-time that propagate outward at the speed of light. He doubted they would ever be detected because the distortions they produce are fantastically small. The first detected gravitational wave stretched and compressed the 4-kilometer arms of the LIGO detector by less than 1,000th the diameter of a proton. Yet on September 14, 2015, the LIGO detectors registered exactly this: a signal produced by two black holes, approximately 29 and 36 times the mass of our Sun respectively, spiraling together and merging 1.3 billion light-years away. The collision lasted a fraction of a second. It released more energy than all the stars in the observable universe combined emit in that same instant, almost entirely as gravitational waves, and it moved the detector arms by less than the width of a single atomic nucleus. Then, in June 2023, an international collaboration of pulsar timing arrays, including nanograv, published simultaneous papers confirming something still more remarkable: the detection of a gravitational wave background, a constant, low-frequency hum of gravitational waves permeating the entire universe, produced by the slow spiral of supermassive black holes at the centers of galaxies across cosmic time. We have heard the universe, not as a metaphor, as a pattern in the timing of pulsars, those city-sized spinning neutron stars whose precise ticks were slightly, measurably disturbed by ripples in space-time arriving from across billions of light years. The universe has been humming for a long time. We only recently learned to listen. The black hole at the center of our galaxy is 4 million times the mass of our sun, and we photographed it for the first time in 2022. At the center of the Milky Way, 26,000 light-years from where you are lying right now, there is a supermassive black hole called Sagittarius, a star. Its mass is approximately 4 million times the mass of our sun, compressed into a region smaller than the orbit of Mercury. For decades, its existence was inferred from the behavior of stars near the galactic center, which orbit an invisible massive object at speeds approaching 10,000 kilometers per second, completing their orbits in periods as short as 12 years. The astronomer Andrea Ghez and her team at UCLA tracked these stars for 30 years, work for which she shared the Nobel Prize in Physics in 2020. Then, on May 12, 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius, a star, a ring of glowing hot gas surrounding a dark central shadow, the silhouette of the event horizon, the point beyond which nothing escapes. The image, built from data collected simultaneously by radio telescopes across the planet, from Hawaii to the South Pole, shows a blurry orange ring 52 micro-arc-seconds across. It took 5 years of computing to process. The black hole itself is invisible by definition. What you see in the image is the last light, orbiting just outside the boundary of no return, heated to billions of degrees by the violence of its own infall. Sagittarius, a star, is, at this moment, relatively quiet, but the gas and dust at the center of our galaxy suggest a more active past, and it will become active again. The Milky Way, like every galaxy, has a sleeping giant at its heart. The Milky Way and Andromeda will collide in approximately 4.5 billion years, and the collision will be surprisingly quiet. The Andromeda Galaxy, the nearest large galaxy to our own, a spiral containing roughly 1 trillion stars, is approaching the Milky Way at approximately 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide. Not crash, exactly. Collide. The distinction matters because galaxies are almost entirely empty space. When two galaxies merge, their stars almost never physically strike each other. The distances between stars are so vast, the nearest star to our sun is 4.2 light-years away, roughly 40 trillion kilometers, that two entire galaxies can pass through each other with extraordinarily few direct stellar collisions. What happens instead is gravitational choreography on a cosmic scale. Stars are flung into new orbits. New regions of gas compression trigger bursts of star formation. The distinctive spiral arms of both galaxies are disrupted and gradually blended, simulations of the Milky Way. Andromeda merger, now highly refined with data from the Gaia spacecraft's precision measurements of stellar positions and velocities, suggests that the first close passage will occur in about 4.5 billion years, followed by a second and then a gradual merger into a single large elliptical galaxy, sometimes nicknamed Milkomeda, over the following billions of years. The Sun will almost certainly survive this process, though it will likely be in a very different part of the merged galaxy by the end. Earth may or may not still exist by then. What is certain is that the night sky of anyone present for the collision will be the most spectacular thing any sentient being has ever witnessed. Galaxies lit up across the sky, new constellations forming over millions of years. The view alone worth the wait. Rogue planets, worlds with no sun, may outnumber stars in the galaxy. Not every planet orbits a star. Some are ejected from their solar systems during the chaotic early dynamics of planetary formation, flung outward by gravitational interactions with larger planets until they escape entirely, drifting into the interstellar dark. These are called rogue planets or free-floating planets, and they are far more numerous than most people know. Estimates based on gravitational microlensing surveys, which detect the brief brightening of background stars as a massive object passes in front of them, have suggested that the Milky Way may contain as many as several 100 billion rogue planets, possibly outnumbering stars. In 2023, the James Webb Space Telescope captured something extraordinary in the Orion Nebula, roughly 540 paired objects, each of planetary mass, drifting through the stellar nursery together in binary pairs. These Jupiter mass binary objects, dubbed jumbos, were unexpected and remain only partially explained. They are of planetary mass, between 1 and 13 times the mass of Jupiter, yet they float free of any star, paired together gravitationally in binary pairs in ways that do not fit standard planetary formation models. How planetary mass objects came to exist in pairs without a parent star is genuinely unexplained. The universe, it appears, contains an enormous population of cold, dark, starless worlds, some perhaps retaining enough internal heat to keep subsurface oceans liquid for billions of years, warmed not by a distant sun, but by the slow release of their own primordial heat and radioactive decay. Life as we understand it requires energy, but energy, it turns out, does not always have to come from above. There may be worlds in the dark that have never seen a star and never needed to. The Great Attractor is a mysterious mass pulling our galaxy and hundreds of others toward a single point at speeds we cannot fully explain. In the 1970s and 1980s, astronomers studying the peculiar motion of galaxies in our cosmic neighborhood noticed something troubling. The Milky Way, along with the Andromeda Galaxy and dozens of other members of our local group, is moving in a direction that cannot be fully explained by the expansion of the universe or the gravity of nearby visible matter. Something is pulling us. The source of this gravitational attraction, located in the constellation Centaurus approximately 250 million light-years away, came to be called the Great Attractor. It lies frustratingly close to the plane of the Milky Way's disk, a region so dense with the dust and gas of our own galaxy that optical telescopes cannot see through it, a zone astronomers call the zone of avoidance. X-ray and radio observations have since partially mapped the region, revealing an enormous supercluster of galaxies called the Norma cluster at or near the Great Attractor's location. But the Great Attractor itself may be only one component of a larger structure. Further mapping has identified an even more massive concentration beyond it, the Shapley supercluster, 650 million light-years away, which appears to be the dominant gravitational influence on our region of the universe. The Milky Way, the local group, the Virgo supercluster to which we belong, and thousands of other galaxy clusters are all being drawn, slowly and irresistibly, in the same direction. We do not know exactly where it leads. We know only that we have always been falling toward it at millions of kilometers per hour, in the direction of something enormous that we cannot yet fully see. The Bhuta's void is a region of space 330 million light-years across that contains almost nothing at all. The universe is not uniformly filled with matter. Galaxies cluster along vast filaments and sheets, surrounding immense voids where almost no matter exists. The largest and most studied of these voids was discovered in 1981 when astronomers Robert Kirshner, Augustus Umler, Paul Schechter, and Stephen Schechtman conducted a survey of galaxies in the direction of the constellation Bhutas and found almost nothing. A roughly spherical region approximately 330 million light-years across, one of the largest known voids in the observable universe. containing only a handful of galaxies where thousands would be expected. If the Milky Way were located at the center of the Botas void, the night sky would be almost completely dark. The nearest galaxy would be hundreds of millions of light years away. Our galaxy might have developed astronomy far later because there would be little to observe. The nearest quasars, the nearest galactic clusters, the nearest structural markers of the universe, all hidden by the sheer emptiness of the void. The Botas void is not technically empty. It contains gas and dark matter and the occasional isolated galaxy. But on the scale that matters cosmologically, it is as close to true emptiness as anything the observable universe offers. And it is, in a way, calming. The universe is mostly nothing. The things, the stars, the planets, the galaxies, the minds that look at them, are the minority. What surrounds and dwarfs all of it is the quiet of space, patient and vast and almost entirely empty, stretching in all directions from wherever you happen to be. The large-scale structure of the universe looks almost exactly like a human brain, and this is not a coincidence scientists have been able to ignore. When cosmologists map the distribution of galaxies across hundreds of millions of light years, something startling emerges. Galaxies do not scatter randomly through space. They cluster along vast filaments of dark matter and gas, long, glowing threads connecting dense nodes where galaxy clusters congregate, surrounding enormous voids where almost nothing exists. This three-dimensional structure, called the cosmic web, is the largest known structure in the universe, a scaffolding that spans the entire observable cosmos. In 2020, researchers published a direct visual comparison between high-resolution images of the cosmic web and microscopy images of a human cerebral cortex. The similarity was so precise that it prompted a quantitative analysis. Network scientists measured the clustering of nodes, the distribution of filament lengths, the fraction of volume occupied by structure versus void. The numbers were nearly identical. The universe at its largest scale and the brain at its smallest scale organize their matter in the same way. This is not because they share a physical mechanism. The forces involved are entirely different. Gravity operating over billions of light years, electrochemistry operating across micrometers. It is because the mathematics of network organization tends to converge on similar solutions across wildly different scales. The universe is not shaped like a brain, but something in the way complex systems organize themselves, something in the deep structure of how things connect, produces the same pattern whether the things connecting are galaxies or neurons. You contain, folded inside your skull, a structure that echoes the largest thing in existence, and the largest thing in existence bears the silhouette of you. The Oort Cloud is the true outer boundary of our solar system, and we have never directly seen it. Most people think of the solar system as ending somewhere around Neptune, the outermost of the 8 planets, about 4.5 billion kilometers from the Sun. But this is only the inner solar system. Beyond Neptune lies the Kuiper Belt, a disk of icy objects including Pluto. And beyond that, far, far beyond that, lies the Oort Cloud, a vast, roughly spherical shell of icy bodies thought to surround the solar system at distances between roughly 2,000 and 100,000 astronomical units from the Sun. The outer edge of the Oort Cloud is believed to extend nearly 2 light-years from the Sun, almost halfway to the nearest star. The Oort Cloud has never been directly observed. We infer its existence from the behavior of long-period comets, those sweeping visitors that appear in our sky once in a millennium and take thousands of years to complete a single orbit. They come from somewhere enormously distant, perturbed by the gravitational influence of passing stars or the tidal forces of the Milky Way's disk, and they fall inward toward the Sun after sleeping undisturbed in the cold dark for billions of years. The Oort Cloud is thought to contain trillions of these dormant objects. the leftover rubble from the solar system's formation, stored in the deep cold at the very edge of what belongs to our sun. Voyager 1, the farthest human-made object ever launched, will not reach the inner edge of the Oort Cloud for another 300 years. It will take 30,000 years to pass through it. The solar system is much larger than the solar system you were taught about. Most of it is silent, frozen, and entirely unseen. The overview effect, what happens to the human mind when it sees Earth from space, may be the most important thing astronauts bring home. Since the first humans orbited Earth, a remarkably consistent experience has been reported by astronauts from different countries, different missions, and different personal backgrounds. Looking down at Earth from orbit, or farther, from the Moon, produces a cognitive and emotional shift that many describe as among the most profound experiences of their lives. The philosopher Frank White, who interviewed dozens of astronauts in the 1980s, named it the overview effect, the sudden, visceral understanding that Earth is a single unified system, that the borders between nations are invisible and irrelevant from space, that the thin blue line of atmosphere is fragile and finite in a way no photograph adequately conveys. Edgar Mitchell, who walked on the Moon during Apollo 14 in 1971, described a sudden sense of universal connectedness he spent the rest of his life trying to articulate. Ron Garan, who spent time on the International Space Station, described the experience as a sobering contradiction, the beauty of Earth from above against the knowledge of the suffering occurring on its surface. More recent astronauts from commercial missions have described breaking into tears without expecting to. The overview effect is not uniform, and not everyone reports it identically, but the pattern is consistent enough to be recognized as a real psychological phenomenon studied by researchers at institutions including NASA and the University of Pennsylvania. What it may represent is the human mind encountering a perspective it evolved without, a view from outside the system it was built inside, and briefly, in the silence of orbit, above the curve of a world that suddenly looks like home precisely because it looks so small, understanding something it cannot quite put back the way it found it. Dark matter makes up 27% of the universe, and after decades of searching, we still do not know what it is. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a discovery that has not been resolved to this day. The outer edges of spiral galaxies orbit their centers at speeds that should be impossible given the amount of visible matter present. If only the stars, gas, and dust we can see were contributing to the galaxy's gravity, the outer stars should be moving much more slowly. The same way the outer planets of our solar system orbit the sun more slowly than the inner ones. They don't. They move at roughly the same speed as stars near the center. The only explanation that fits is that there is a vast amount of additional mass distributed throughout and around the galaxy in a form that does not emit, absorb, or reflect light. This invisible mass came to be called dark matter, and subsequent observations have confirmed its presence in multiple independent ways. The bending of light from distant objects by more gravity than visible matter can produce, the temperature fluctuations in the cosmic microwave background, the behavior of galaxy clusters in collisions. Dark matter makes up approximately 27% of the total mass energy content of the universe. Ordinary matter, every star, planet, moon, gas cloud, and living thing, makes up only about 5%. The remaining 68% is dark energy. We have no confirmed direct detection of a single dark matter particle. Experiments deep underground in old mines, orbiting detectors in space, and particle colliders have searched for decades. Nothing confirmed. The dominant component of all structure in the universe remains, at this moment, completely mysterious. Dark energy is accelerating the expansion of the universe, and it makes up 68% of everything that exists. In 1998, two independent teams of astronomers studying distant Type 1a supernovae, a type of stellar explosion used as a standard candle for measuring cosmic distances, made a discovery that genuinely shocked the physics community. The universe was not just expanding, as Edwin Hubble had demonstrated in the 1920s. It was accelerating. The expansion was speeding up over time, driven by some form of energy inherent to space itself that was pushing galaxies apart faster and faster. This force, or property, or phenomenon, depending on how you approach it theoretically, was named dark energy, and it makes up approximately 68% of the total mass energy content of the observable universe. The discovery won the 2011 Nobel Prize in Physics. What dark energy actually is remains one of the deepest unsolved problems in all of science. The simplest explanation, that it is the energy density of empty space, a cosmological constant that Einstein actually proposed and then famously retracted, fits the data well, but provides no physical mechanism. More exotic explanations, including a dynamic field called quintessence or modifications to the theory of gravity itself, remain possible. What is known is the effect every galaxy cluster, every group of galaxies, every pair of galaxies not bound together by their own gravity is moving away from every other at an accelerating rate. In the very long future, the universe will become increasingly empty as distant galaxies recede beyond our cosmic horizon. The stars will go dark one by one, and all that will remain is the dark energy still pushing in a universe that has become too sparse to notice. The Hubble tension. The universe appears to be expanding at two different rates depending on how you measure it, and no one knows why. One of the most significant and unsettling problems in modern cosmology is a number, or rather, two numbers that should be the same and are not. The Hubble constant, the rate at which the universe is expanding, expressed as the speed of recession per unit of distance, can be measured in two fundamentally different ways. The first is to look backward, analyze the cosmic microwave background, and use our understanding of early universe physics to predict what the expansion rate should be today. This method, refined by the Planck satellite, yields a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second is to look outward, measure the distances and recession speeds of nearby galaxies using Cepheid variable stars and Type 1a supernovae as distance markers. This method, refined by teams using the Hubble Space Telescope and now the James Webb Space Telescope, consistently yields approximately 73 kilometers per second per megaparsec. These two values differ by about 8%, a discrepancy of roughly 4 to 5 sigma in statistical significance, which in physics is the threshold for claiming a discovery. It is too large to be explained by measurement error alone, and both methods have been checked, rechecked, and refined for decades. Either the measurements contain a subtle systematic error that no one has identified, or there is new physics operating in the universe that our current models do not account for. This discrepancy, called the Hubble tension, is not a minor footnote. It is a crack in the standard model of cosmology, a hint perhaps that the universe is doing something we do not yet understand. Fast radio bursts are millisecond flashes from across the universe, and in 2025, most of them remain unexplained. In 2007, astronomers analyzing archival data from the Parkes Observatory in Australia found something that had been recorded years earlier and not immediately recognized, a burst of radio waves lasting approximately 5 milliseconds that appeared to originate from far outside the Milky Way. The signal had the characteristics of having traveled through enormous amounts of intergalactic plasma, the thin soup of charged particles between galaxies, suggesting a source billions of light years away. It was called a fast radio burst. Since then, hundreds more have been detected. Many are one-time events, never repeating. Some repeat on timescales of days or weeks. The most active repeater, FRB 201211102A, has produced over 1,600 bursts in 47 days. The sources of most fast radio bursts have been traced to distant galaxies, and at least some appear to be associated with magnetars, those extraordinary neutron stars with extreme magnetic fields. In 2020, a fast radio burst was detected from within our own galaxy, traced directly to a known magnetar, SGR 1935+2154, providing the first definitive identification of at least one type of source. But not all fast radio bursts fit the magnetar template. Some originate in regions inconsistent with magnetar formation. The variety of observed properties suggests that fast radio bursts may have multiple types of progenitors, or that the universe is doing something in the radio frequency range that we have only recently developed the technology to notice and do not yet have the theoretical framework to fully explain. Quasars are the brightest objects in the universe, powered by supermassive black holes consuming matter at extraordinary rates. In the 1950s and 1960s, radio telescopes detected intense sources of radio emission that, when examined with optical telescopes, appeared as faint point sources of light like very dim stars. But their spectra, the breakdown of their light by wavelength, were wrong for stars. The spectral lines were shifted so far toward the red end of the spectrum that, if the shift was interpreted as a Doppler effect of cosmic expansion, these objects were not just far away, they were billions of light years away. At that distance, to be detectable at all with mid-20th century instruments, they had to be extraordinarily luminous. These quasi-stellar radio sources, shortened to quasars, are now understood to be the most energetically active phase in the life of certain galaxies, a period when the supermassive black hole at a galaxy's center is actively consuming enormous quantities of gas and dust, converting a fraction of that mass directly into energy with an efficiency far exceeding nuclear fusion. A quasar can outshine its entire host galaxy, hundreds of billions of stars, by a factor of 1,000 or more. The most luminous quasar currently known, J0529-4351, discovered in 2024 using data from the European Southern Observatory, is estimated to consume the equivalent of 1 solar mass per day and has a luminosity roughly 500 trillion times that of our Sun, making it the brightest known object in the universe. Quasars were most common in the universe between roughly 2 and 3 billion years after the Big Bang, when the raw material for black hole feeding was more abundant. The Milky Way's own central black hole once passed through a quasar phase. The sleeping giant at the center of our galaxy was once one of the brightest things in the universe. The James Webb Space Telescope is revealing that the early universe made galaxies far too large, far too soon, and this may require revising what we know. One of the early, unexpected findings of the James Webb Space Telescope, which began science operations in mid-2022, was the detection of galaxies at redshifts corresponding to the first few hundred million years of the universe's existence. Galaxies that appear to contain stellar masses significantly larger than existing models of galaxy formation predicted should be possible at such early times. The Standard Model of Cosmology, Lambda CDM, describes how the universe's structure grows hierarchically. Small structures form first, then gradually merge into larger ones. Galaxies in the very early universe were expected to be small, irregular, and diffuse. Some of the galaxies JWST found appear to be more massive, more structured, and in some cases more similar to mature modern galaxies than models predicted. Papers published between 2022 and 2025 described candidate objects at redshifts above 10, corresponding to times less than 500 million years after the Big Bang, with inferred stellar masses that strained the Standard Model's predictions. The implications are not fully resolved. Some objects initially flagged as problematic have been recategorized as less extreme after more careful spectroscopic analysis. But the pattern of finding more structure earlier than expected has persisted across multiple JWST observing campaigns. It may represent a genuine challenge to the standard model, requiring new physics in the early universe. Or it may represent the growing pains of a new instrument, revealing the true complexity of what was always there. Either way, the early universe is not what we thought it was, and the telescope that was built to look back further than any before it is delivering what its builders hoped. Genuine surprise. Voyager 1 is the farthest human-made object in existence, and it is now more than 24 billion kilometers from the Sun. On September 5, 1977, NASA launched a spacecraft the size of a small car called Voyager 1, programmed to fly past Jupiter, Saturn, and their moons using the gravitational assistance of each planet to accelerate it outward. It has been traveling ever since. As of 2025, Voyager 1 is more than 24 billion kilometers from the Sun, roughly 160 times the Earth-Sun distance, a unit called an astronomical unit. It crossed the heliopause, the boundary where the Sun's solar wind is overcome by the interstellar medium, in August 2012, becoming the first human-made object confirmed to be in interstellar space. Radio signals from Voyager 1 take more than 22 hours to reach Earth, traveling at the speed of light. The spacecraft is powered by radioisotope thermoelectric generators that continue to produce electricity from the decay of plutonium-238, though power levels have declined over decades and NASA has had to shut down scientific instruments one by one. In late 2023, Voyager 1 began sending corrupted telemetry data back to Earth, and engineers spent months diagnosing and resolving what turned out to be a single faulty chip in one of its 3 onboard computers. They did it. In April 2024, Voyager 1 resumed sending readable data from interstellar space, 46 years after launch, from a distance at which round-trip communications take 45 hours. The spacecraft carries a gold-plated record containing sounds, music, and images from Earth. A message from a young, optimistic species to whoever might someday find it in the incomprehensible distances between the stars. The Fermi paradox asks a simple question. If the universe is so vast and so old, where is everyone? In the summer of 1950, physicist Enrico Fermi was eating lunch with colleagues at Los Alamos National Laboratory, and the conversation turned to extraterrestrial intelligence. Recent news stories had discussed flying saucer sightings. Someone joked about alien visitors, and Fermi, one of the most brilliant physicists of the 20th century, looked up and said, "But where is everybody?" The question was so simply phrased and so devastatingly pointed that it has been discussed by scientists, philosophers, and storytellers ever since. The universe is approximately 13.8 billion years old. Our sun is 4.6 billion years old. There were stars and planets forming billions of years before our solar system existed. If intelligent life arose elsewhere, even once, in a galaxy this old and this vast, the civilization could theoretically have colonized the entire galaxy in a few million years. A span that is nothing on cosmic timescales, and yet there is no evidence of anyone. No signals. No megastructures. No detectable signs of technological activity anywhere in the observable universe. The silence is as complete as the darkness between the stars. Proposed resolutions are numerous. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations self-destruct before becoming interstellar. Perhaps they are communicating in ways we cannot detect. Perhaps the distances are simply too vast for any practical contact. None of these resolutions has been confirmed. The question Fermi asked over lunch remains, nearly 75 years later, completely unanswered. And tonight, as you lie here on a quiet planet, under a silent sky, it is still one of the most important questions the universe has ever asked of itself. The WOW signal, a 72-second transmission received in 1977, remains the most compelling candidate for an extraterrestrial signal ever detected. On August 15, 1977, astronomer Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope when he came across a series of alphanumeric characters that so excited him he circled them with a red pen and wrote "Wow" in the margin. The signal lasted 72 seconds, the full duration the source spent in the telescope's beam as Earth rotated, and it exhibited precisely the characteristics that SETI researchers had specified should characterize a deliberate narrow-band transmission from an extraterrestrial civilization. It originated from the direction of the constellation Sagittarius, at a frequency very close to the 1,420 MHz hydrogen line, the frequency that radio astronomers had long argued an intelligent civilization might choose for interstellar communication, since hydrogen is the most abundant element in the universe, and its emission frequency would be a natural choice for a shared cosmic language. The signal has never been detected again, despite numerous attempts over nearly 5 decades using both the original site and far more sensitive instruments. In 2020, a team of amateur astronomers identified a pair of sun-like stars, 2-mass 1928198-2-26400123 and 2-mass 1929018-2629595, as possible candidates for the signal's origin, though no confirmation exists. The WOW signal may have been a natural phenomenon. It may have been interference. It may have been a one-time transmission from a source that will never repeat. It remains, nearly 48 years after the ink dried on that margin, the most suggestive and most persistently unexplained candidate signal in the history of the search for extraterrestrial intelligence. The TRAPPIST-1 system has 7 Earth-sized worlds, 3 in the habitable zone, orbiting a star smaller than the Great Red Spot. In 2017, NASA announced the discovery of 7 Earth-sized planets orbiting a dim red dwarf star called TRAPPIST-1, located approximately 40 light-years from Earth in the constellation Aquarius. 7 rocky planets, all roughly the size of Earth, orbiting a star so small, roughly the size of Jupiter, only slightly larger than the Great Red Spot storm on Jupiter's surface, that all 7 planets orbit closer to their star than Mercury orbits our Sun. Yet because TRAPPIST-1 is so dim and cool, the inner planets receive tolerable amounts of heat. 3 of the planets, designated TRAPPIST-1e, 1f, and 1g, orbit within the star's habitable zone, the range of distances where liquid water could theoretically exist on a planetary surface. Subsequent observations, including early results from the James Webb Space Telescope between 2023 and 2025, have begun characterizing the planet's atmospheres. JWST observations of TRAPPIST-1b, the innermost planet, found no evidence of a thick atmosphere, suggesting at least that planet may be airless. The more promising candidates, E, F, and G, remain to be characterized in detail. The system is extraordinary for its compactness and the number of potentially habitable worlds in such proximity. Standing on the surface of TRAPPIST-1e, if it has a surface, the other planets would be visible to the naked eye as disks, not points. Worlds in close enough proximity to one another that they would appear as other moons in the sky. It is, by the standards of planetary science, a very crowded neighborhood, and 3 of its members may have oceans. Our Sun will become a red giant in about 5 billion years, and when it does, it will swallow everything you have ever known. The Sun is a middle-aged star. It formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust and it has been fusing hydrogen into helium in its core ever since, releasing the energy that warms every ocean and drives every weather system on Earth. It will continue to do so for approximately another 5 billion years. Then the hydrogen in the core will run out. The core will begin to contract and heat, triggering hydrogen fusion in a shell around it. The outer layers will expand dramatically. The sun will become a red giant, swelling to a radius perhaps 200 times its current size. In its expanded state, it will likely absorb Mercury, then Venus, then possibly Earth. Models differ on whether Earth will be engulfed or merely scorched, its oceans long since evaporated. What is certain is that by the time the red giant phase begins, roughly 1 billion years from now, the sun's increasing luminosity will have already rendered Earth's surface too hot for liquid water. The window for life on Earth, measured on a geological timescale, may be less than 1 billion years from now. After the red giant phase, the sun will shed its outer layers in a beautiful expanding shell of ionized gas called a planetary nebula, and the core will remain as a white dwarf, a dense, slowly cooling ember roughly the size of Earth, carrying the carbon and oxygen forged in the sun's interior. The light of our star, in the end, compressed to a crystal, still shining, but no longer warm, still there, but no longer ours. Panspermia, the idea that life may travel between worlds, is a serious scientific hypothesis, not science fiction. The question of how life began on Earth is one of the deepest in all of science, and it remains genuinely open. One hypothesis that has moved from the fringes toward more serious consideration is panspermia, the idea that life, or the building blocks of life, or the spores of microbial life, can travel between planetary systems aboard meteorites or comets, seeding new worlds with biology from old ones. The evidence supporting at least the plausibility of panspermia has grown in recent decades. Meteorites of confirmed Martian origin have been found on Earth. Rocks blasted from the Martian surface by asteroid impacts traveled through space for millions of years and survived the fiery passage through Earth's atmosphere. Amino acids and other organic molecules have been found inside meteorites from primitive asteroid families, showing that the chemical precursors of life are widespread in the cosmos. Experiments have demonstrated that certain extremophile bacteria can survive in the radiation and vacuum of space for extended periods when shielded inside rock. And the late heavy bombardment, a period of intense asteroid and comet impacts on the inner solar system roughly 4 billion years ago, would have provided both the mechanism for ejecting material between planets and the delivery system for organic chemistry. Whether life itself has transferred between worlds remains unproven, but the molecules of life are common in space. The shuttles that could carry them exist. The question is not whether the mechanism is possible, it is whether anyone was aboard. The universe had to be almost precisely the way it is for any of us to exist, and the reasons why are not fully understood. The physical constants of the universe, the strength of gravity, the charge of an electron, the ratio of the masses of the proton and neutron, the cosmological constant governing dark energy appear to be set with extraordinary precision for the existence of complexity, chemistry, and life. Change the strength of the strong nuclear force by a few percent, and atomic nuclei could not form, or carbon could not be synthesized in stellar interiors. Change the cosmological constant by a small amount, and the universe either collapses back in on itself or expands so rapidly that no structure forms at all. Change the ratio of electromagnetic force to gravity, and stars cannot form with stable properties. This apparent fine-tuning is called the anthropic principle, and it is one of the most philosophically contentious topics in all of science. Some scientists argue that the fine-tuning is an illusion, that we observe a universe compatible with our existence because we could not observe any other. If there are many universes with different constants, a multiverse, then we necessarily find ourselves in one of the rare compatible ones. Others argue that a deeper theory will eventually explain why the constants must have the values they do, reducing the apparent fine-tuning to necessity. Others see in it something more. Whatever its explanation, the fine-tuning is real in this sense. The universe could have been many things. It is the specific thing that allows stars to burn, carbon to form, planets to cool, and minds to eventually arise and look up and wonder how any of it came to be. The universe that produced you was not just any universe. It was this one, the one with the right numbers, however they got that way. The last stars in the universe will die approximately 100 trillion years from now, and what comes after is stranger still. The universe is currently in what cosmologists call the stelliferous era, the age of stars. It began about 100 million years after the Big Bang, when the first stars ignited, and it will end approximately 100 trillion years from now, when the last stars exhaust their fuel and go dark. The longest-lived stars are the smallest. Red dwarf stars, with masses around 1/10 that of the Sun, burn their hydrogen so slowly and so efficiently that some of them will live for 10 trillion years. Our Sun will last about 10 billion years total. The most massive stars, hundreds of times the Sun's mass, last only a few million years. But the red dwarfs, dim, cool, barely luminous, will outlast everything else in the galaxy, burning steadily long after every brighter star has died, their faint orange glow the last light in an increasingly dark universe. When they too finally exhaust their hydrogen and cool to dark remnants, the universe will enter the degenerate era, a period lasting perhaps 10 to the power of 40 years, a number with 40 zeros, during which the universe contains only white dwarfs, neutron stars, and black holes, slowly cooling and decaying. Then, the black hole era, a period of 10 to the power of 100 years, during which supermassive black holes dominate what remains, and then even the black holes evaporate via Hawking radiation, a quantum process so slow it defies imagination. What remains after the last black hole evaporates is the dark era, a universe at maximum entropy, containing only diffuse radiation and perhaps the occasional random quantum fluctuation. The universe, in the end, does not explode or collapse. It simply, very slowly, runs out. It fades. It becomes quiet in a way that makes tonight seem briefly, beautifully loud. The Boltzmann brain, a thought experiment about what happens at the end of time, is one of the strangest ideas in all of cosmology. In the far future, long after the last stars have died and even the black holes have evaporated, the universe will exist in a state of near maximum entropy, a near featureless expanse of diffuse radiation, random quantum fluctuations, and the fading echoes of structure. In this state, physicist Ludwig Boltzmann noted in the 19th century, random thermal fluctuations will occasionally produce, by chance alone, any configuration of matter or energy, including improbably complex ones. In a universe with infinite time ahead of it, even highly improbable events are not only possible, but inevitable. A modern extension of this idea asks, in such a universe, which is more likely to arise from a random fluctuation, a full physical universe with all its billions of years of evolution, or a single conscious brain suspended in the void, with all the memories of a full life already formed, experiencing a single moment of awareness before dissolving back into randomness? Statistical arguments suggest that the latter, a Boltzmann brain, would arise vastly more frequently because it is a much smaller fluctuation. This creates a philosophical problem. If Boltzmann brains are more likely than ordinary observers, why do we appear to be ordinary observers with a consistent physical universe behind us? The argument is used to test cosmological models, A model that predicts more Boltzmann brains than ordinary observers is considered to have a problem. It is one of those ideas at the edge of physics where mathematics and metaphysics become difficult to separate. And lying here in the quiet dark on a small planet in a middle-aged galaxy, it is, in its strange way, a reminder the universe did not have to make something as intricate and persistent as you. That it did is, from the perspective of sheer improbability, remarkable. Cosmic time is so vast that all of human history occupies less than 1 second on the universal calendar. Carl Sagan introduced the cosmic calendar in his 1980 television series, Cosmos, a thought experiment in which the entire 13.8 billion year history of the universe is compressed into a single calendar year. On this calendar, January 1st is the Big Bang. The Milky Way forms in mid-May. Our solar system forms in early September. The first life on Earth appears in mid-September. For most of October and November, the Earth is inhabited only by single-celled organisms. The Cambrian explosion, the sudden diversification of complex multicellular life, occurs in mid-November. Dinosaurs arrive on December 10th and go extinct on December 26th. All of recorded human history, the pyramids, Rome, the printing press, the Industrial Revolution, everything humans have ever written down occurs in the last 10 seconds of December 31st. Every person you have ever known or heard of lived and died in the final tick of the final second of the final minute of the final hour of the year. This is not a metaphor for insignificance. It is a metaphor for what it means to be early. Intelligent life on Earth has existed for an eye blink relative to the age of the universe. The universe will continue, if models are correct, for timescales that make its current 13.8 billion year age look like the first morning of a very long life. Whatever we do or fail to do, whatever we build or neglect or wonder about, happens at the very beginning of what may be an almost incomprehensibly long story. We are, on any cosmic scale, extremely young. We have, on any cosmic scale, nearly everything ahead of us. The universe contains approximately 2 trillion galaxies, and each one is a story too long to tell. For most of the 20th century, astronomers estimated the number of galaxies in the observable universe at roughly 200 billion. A number derived from Hubble Space Telescope deep field images taken in the 1990s, which counted all the galaxies visible in small patches of sky and extrapolated across the whole. In 2016, a team led by astronomer Christopher Consolis at the University of Nottingham published a revised estimate using data from surveys across the electromagnetic spectrum. The actual number of galaxies in the observable universe is approximately 2 trillion, 10 times the previous estimate. The discrepancy arises because the earlier counts missed the enormous number of faint, small, diffuse galaxies that were too dim or too distant to be detected in earlier surveys. 2 trillion galaxies, most of them containing hundreds of billions of stars. Most of those stars accompanied by planets. The numbers grow large enough that the imagination simply stops. What the mind does not stop, and perhaps should not stop, is the quieter observation. Each of those 2 trillion galaxies is an object of extraordinary complexity. Each has a history that began near the Big Bang, a structure that took billions of years to assemble, a center and a core and arms and clusters and the light of billions of suns. We have named perhaps a few thousand of them. We have photographed perhaps 1 million in any detail. 2 trillion stories, most of them untold, most of them unwitnessed, playing out in the dark between points of light that human beings have been looking at since they first had eyes to look. And from here, they look like stars. Light from the most distant objects we can see left its source before Earth existed. The James Webb Space Telescope has detected light from galaxies at redshifts corresponding to the first few hundred million years of the universe's life. objects so distant that the light now arriving in our instruments has been traveling for more than 13 billion years. The galaxy currently holding the confirmed redshift record as of 2025 is JD's GS Z140, with a spectroscopically confirmed redshift of approximately 14.32, corresponding to a time roughly 290 million years after the Big Bang. When that light began its journey, there was no solar system, no Earth, no sun. There were no rocky planets anywhere in the observable universe. The heavy elements required to build them had not yet been produced in sufficient quantities by dying stars. The light that entered the James Webb Space Telescope's mirrors carried information about a universe that was not yet capable of producing anything like us. It traveled across an expanding universe for 13.4 billion years, arriving at a telescope built by a species that evolved in the last cosmic instant on a world that formed from the remnants of stars that did not yet exist when the light began its journey. The act of looking at the deep sky is not simply an act of distance. It is an act of time travel in the truest available sense. Every photograph of the early universe is a photograph of the past, and the past in this case is older than the ground beneath you, older than the elements in your body, older than anything in the solar system. It is the universe before it knew what it would become. You are, from the perspective of the cosmos, made of stardust, and this is not a poetic metaphor, it is chemistry. The hydrogen in your body, in the water in your cells, in the organic molecules of your DNA, was formed in the first 3 minutes after the Big Bang. It is the oldest material in you, nearly 13.8 billion years old. The helium in trace amounts in your body has a similar origin, but every other element, every carbon atom in every molecule of every cell, every oxygen atom you are breathing right now, every calcium in your bones, every iron in your blood, every phosphorus in your DNA was forged inside a star that lived and died before the sun was born. Carbon and oxygen are produced in the nuclear burning stages of medium-mass stars like the Sun, released when they shed their outer envelopes as planetary nebulae. Silicon, sulfur, and the heavier elements are produced in the final evolutionary stages of more massive stars and dispersed when those stars explode as supernovae. Iron, the endpoint of stellar nucleosynthesis, the element at which nuclear fusion no longer produces net energy, is so abundant in the universe because it is the final product of a massive star's life released in the supernova blast that ends it. When you look at the iron in your blood, you are looking at the terminal product of a stellar furnace, the ash of nuclear fires that burned for millions of years in a star that died before our solar system existed. Carl Sagan said, "We are made of star stuff." It is not a metaphor for being connected to the cosmos. It is a literal description of your biochemistry. You are, in the most concrete sense, the universe looking at itself. You are still moving at this exact moment, and this is what that means. We began tonight with motion, and halfway through, it is worth returning to it. Not as a fact to be learned, but as a thing to be felt. Right now, as you lie here, you are on a planet spinning at over 1,000 kilometers per hour, orbiting a star at over 100,000, sweeping through a galaxy at close to 1,000,000, falling toward a great attractor you will never see at millions of kilometers per hour. Every atom in your body has been in motion since the Big Bang. The hydrogen in your body has never been still for a single moment in 13.8 billion years. It formed in the first 3 minutes of the universe, spent billions of years in interstellar clouds, collapsed into stars, was released in stellar deaths, drifted through the galaxy, collapsed again into the solar nebula, was incorporated into the chemistry of a young planet, passed through oceans and atmosphere and the bodies of organisms too numerous to count, and arrived finally here, in you tonight, moving at 1,000,000 kilometers per hour through the dark, lying perfectly still. The stillness you feel right now is the most relative stillness in the universe. The motion you cannot feel is among the most absolute. There is something quietly extraordinary about that, about the fact that all this cosmic momentum, all this vast and ancient velocity has arrived at this particular arrangement, you, here, now, almost asleep, and declared it a moment worth having. The most profound fact about the universe may be that it produced something capable of asking questions about it. The universe is 13.8 billion years old. For all but the last few 100,000 years of that time, the blink that includes all of human prehistory and history, there was nothing in it capable of registering its own existence as a fact worth noting. Stars burned without observation, galaxies formed and merged without witness. The cosmic microwave background traveled for billions of years through a universe in which no mind had yet formed to detect it. And then, on one small rocky planet orbiting one ordinary star in the outer spiral arm of one of 2 trillion galaxies, a process that had been running for billions of years, biological evolution, produced a nervous system complicated enough to generate self-awareness. Something that could not only respond to the universe but ask, what is this? How did it begin? How large is it? What will it become? The universe, through one of its most improbable configurations, began to know itself. Physicists sometimes describe this by saying that we are the universe's way of observing itself. The measurement and the measured are not separate. The consciousness looking at the cosmic microwave background is made of matter that was formed in the same event the CMB describes. The questions being asked about the Big Bang are being asked by products of the Big Bang. There is a strangeness to this that does not diminish with repetition. Something came from nothing, and that something eventually produced the capacity to notice that something had come from nothing. Tonight, in the dark, doing the quietest thing a human being can do, you are a part of that. You are the universe, lying still for a moment in the enormity of itself. And so we arrive at the end of tonight's journey through our universe. You are still moving. Earth is still turning beneath you, still carrying you around the sun, still sweeping through the galaxy at nearly 1,000,000 kilometers per hour. You have not stopped moving since the day you were born. You will not stop until long after you are gone. But right now, in this particular darkness, in this particular stillness that is also motion, you know a little more about where you are. A universe 13.8 billion years old, 2 trillion galaxies, stars that died to build you, a black hole at the center of your galaxy, a hum of gravitational waves arriving from the collisions of things larger than you can hold in your mind. A pale blue dot somewhere in the outer arm of an ordinary spiral galaxy, carrying 8 billion minds through the dark at speeds they cannot feel. The universe is vast. It is ancient. It is, in the parts we have seen, extraordinarily beautiful. And it produced you here, tonight, in the specific configuration of atoms and electricity and memory and wonder that allows you to know that any of this is true. Let the motion carry you now. Let the dark do what the dark always does, and let the universe keep its watch over whatever small, warm, temporary thing you are. Sleep well. Thank you for spending this time in our universe with me tonight. This has been Sleepy Science Stories. I'll see you next time.